In this video, we want to discuss what happens when using law of sines to solve a triangle, and we want to investigate some of the other things that can happen, especially when it's not quite so straightforward as some of the previous ones. So as always, let's make a sketch of the information that we're starting with. So we've got an 85-degree angle here. We've got the opposite side, A and little a are opposites, of course. And little b is 25. And usually we start off by saying, well, let's find all the angle measurements, but we only have one this time, so we can't just jump right into that. So we do need to jump right to the formula, and because we have angle measurements that need to be solved for, we're going to put the angles on top in this example of law of sines. So we got sine of 85 over 15. Sine of big B over 25, and the sine of big C over little c. So this one having two variables, we're going to hold off for a minute on that one. We're going to focus on these two, because this is, solved. So if we isolate this to the sine of 85 equals this guy, we can algebraically multiply both sides by 25 to solve for sine of b. And so now we've got sine of b here by itself, and we can punch that into our calculator real quick. So I've got my calculator. I'm going to put this whole expression into there. So that would be the sine of 85 divided by 15 and multiplied by 5, and we get 1.66. Okay? So when we come back to the problem, we put 1.66 here. I hope some alarm bells are going off in your mind, because this doesn't work. This is not a thing. If we recall back from previous units, the sign of the absolute value of sine is always somewhere in between 1 and negative 1. It's got to be less than 1. This number is greater than 1. So this is a big thumbs down, big unhappy face. This is unable to be solved. There is no value of b that would make this work out. And if you don't really believe me, it's all right, of course. Try punching in the inverse sine of that previous answer into your calculator. And, oops, wrong buttons there. The inverse sine of the previous answer, and you will get a domain error telling you that there is no angle whose sine is 1.66. So what this brings up is something called the ambiguous case. Basically, the given information is two sides and an angle not in between them, conventionally known as SSA. Sometimes we use ASS to make students laugh or teachers have a good time, or whatever the case is. But as we get into higher levels of math, this is called the ambiguous case. Ambiguous because there are lots of things that can come up. You're never sure what exactly is going to happen. And it's all based on the actual numbers. There's no one rule. But you have to analyze what's happening based on the size of the angle and the relative sizes of the two lengths of sides that you're given. So let's check that out. Let's kind of check out what can happen. So let's do a little bit of sketching and then kind of play around with what can change and what can't change. So when you're given SSA, you're given some angle, which we'll call A just for sake of simplicity, and you're given some value B next to it, and then the opposite of angle A is side A. So the information in SSA that you're given is little a and little b and big A. An angle, side opposite of it, and one side next to or adjacent to the angle. And so what you really need to consider is a couple of questions. Sorry about that. You need to consider a couple of questions. You need to ask yourself, how big is A? Big A, that is. There's two options. It can be obtuse, or it could be acute. I leave out the option of it being right. If it's a right triangle, none of this really matters because you could just go for SOHCAHTOA and be done with it. And so we don't really consider the option for right triangles because it's not necessary. So big A could be obtuse or it could be acute. Then you want to compare little a and little b, which is, in other words, which is bigger, A or B, or are they equal? And then there is one other thing that could come up, and sometimes it matters this distance right here. And we're going to call this distance h for height. Pretty straightforward, to be honest with you. And h, when A is acute, matters a little bit. When A is obtuse, h is irrelevant. But when A is acute, you're going to need this height. So keep that in mind. But let's talk about h real quick. If you go back to SOHCAHTOA, which we just referenced, h would be the opposite side of big A. Little b here would be the hypotenuse of this green right triangle. So you could say that sine of big A is equal to little h over little b. And so that gives us a nice easy equation for h. Multiply both sides by b. And we get h is equal to the b times the sine of A. And that will become relevant in this SSA case when A is acute. All right, so let's kind of put that on the back burner for now and talk a little bit about when A is obtuse and then come back to it when A is acute. So when A is obtuse, let's do some sketching. First of all, as a reminder, h isn't needed. You'll hopefully see why in just a second. But when A is obtuse, so here's angle A. I'm just going to draw it a little bit obtuse, hopefully to visualize it a little bit. So when A is obtuse, bigger than 90 degrees, we've got little b attached to big A, and then A, little a opposite big A. What do you think has to be the case for A to meet this other side of the angle over here? A has to be strictly greater than B. If A is not greater than B, if A were equal to or less than B, let's kind of start with that same sketch. If A were less than B, it would just be hanging out over here, right? And wouldn't, be big enough to form a triangle. So if A were equal to B, it would just lay on top of it, or it would have to come down over here if it were equal to B, and therefore then it wouldn't be an obtuse angle. So if A is obtuse, and if big A is obtuse, and little a is less than or equal to B, then there is no solution to the triangle. And hopefully the visuals can help you see that. So now let's consider what's going to happen if big A is acute. And this is a slightly more complicated proposition. So let's remember that in the case of A being acute, h is going to be necessary. H is b times the sine of big A. You're going to need that as you start calculating these. And 4 different scenarios come into play here when big A, capital A, is acute. So let's check it out here. So we're going to start in the same way we were starting earlier, with capital A as an acute angle. B is attached to it. And let's label height, because we're going to calculate height whenever A is acute. So there's h. And let's assume for a quick second that A is less than h. So A would just kind of be swinging up here and definitely not big enough to come in contact with the other side down here. So if A is less than h, there is no solution. Doesn't really matter. It's obviously less than B as well, but the important part is that it's less than h. It's not long enough to touch the bottom there. All right. So let's see what happens in another scenario. Let's start with the same picture. Here's angle A, little b attached to it. And let's calculate h. We get some value h. And what would happen if, let's just say that A were equal to h. If A were equal to h, there's one solution. And in fact, it would be a right triangle that you wouldn't necessarily need to use law of sines on. You could go back to toe. All right, so that would be when A is equal to h. Let's take a look at another case. Start with our same acute angle A, adjacent little b, and our h. Now, one of the other options is for A to be longer than B. If A were longer than B, it would have to come out here. That would make this not an acute angle. So therefore, little a would have to exist kind of over here, again, making only one solution. So if little a is longer than little b, there's only one solution. And that leaves us with the most interesting scenario of law of sines with acute angles. And that is when A is longer than h but less than b. So let's kind of start with our same sketch as always. Here's h. And now let's go talk about where A falls. Now, if A is greater than h, it means it has to be somewhere over here. And if it's less than b, you fall between those two. Problem is, if you picture this h as a line of reflection, A could also be that same distance here. And what happens is, if A is between h and b, there are two possible solutions. And that is why SSA is called the ambiguous case. When you're given two sides and a non-included angle, it's a possibility that lots of things can happen. Real quick, before we end this video, I do want to revisit this first problem that we started this video with and talk about it from a new perspective. And in the interest of efficiency, I made the sketch a little bit off camera, but this is essentially what we have, and it's a little more drawn to scale. Sure, 85 is probably a little bit steeper. But because we have an angle and two sides that don't contain the angle, we're going to calculate h. H is always little b times the sine of big A. H is 25 times the sine of 85 degrees. Punch that into your calculator and you get 24.9. Now, check it out and compare A, H, and B. A, I mean, it's kind of irrelevant with what H is, but it's a nice little exercise in comparisons. But A is less than B, and when A is less than B, when A is less than B, it can work out, but A needs to be less than H as well. Since A is less than H, the triangle has no solution.